There is a machine floating in total darkness right now, farther from home than any human creation has ever traveled, and it is still talking to us. It was not built by anyone alive today at NASA. It does not run on solar power, because out where it is, sunlight is basically gone. It runs on less electricity than a small kitchen appliance. And yet, this aging piece of hardware is quietly rewriting some of the most basic assumptions physicists have held about the space beyond our solar system. Researchers are not calling this a small correction. Some are calling it one of the most unexpected findings in modern spaceflight. This machine was supposed to stop working decades ago. Instead, it kept going, and it is still sending back signals that scientists say they did not expect and, in some cases, cannot fully explain. By the end of this video, you will understand exactly what it found, why researchers say it matters for life on Earth, and why 2026 might be the most important year in this machine's entire history. Its name is Voyager 1. If stories like this keep you up thinking about the universe, stay with this channel, because we cover discoveries like this every week. The story starts in September 1977, when engineers at Kennedy Space Center launched a spacecraft with a fairly humble job description: fly past Jupiter, fly past Saturn, take pictures, gather some readings, and then drift quietly into the dark. NASA planners expected the mission to wrap up sometime around 1981. Nobody involved in building Voyager 1 thought they were building something that would still be operating half a century later. But the spacecraft kept performing better than expected at every stage. It reached Jupiter in 1979, and sent home the clearest images of that planet anyone had ever seen. It reached Saturn in 1980, and instead of slowing down, it used the planet's gravity to gain even more speed. By the late 1980s, Voyager 1 had already traveled farther from Earth than any human-made object in history, and its instruments were still working. Engineers who study old spacecraft often describe this as remarkable, because nothing about 1970s technology was designed to survive this long in deep space. Then, in 2012, something happened that changed the entire scope of the mission. Voyager 1 crossed something called the heliopause, and to understand why that matters, you need to picture our solar system a little differently than you probably learned in school. The sun does not just give us light. It constantly sends out a stream of charged particles called the solar wind. That wind blows outward in every direction, and it forms an enormous protective bubble around the entire solar system. Every planet, every moon, every spacecraft we've ever launched sits inside that bubble. At some point, far beyond Neptune, the pressure of that solar wind runs out of strength, and it meets the pressure of the wider galaxy pushing back. That meeting point is the heliopause. Scientists sometimes describe it as the edge of our cosmic neighborhood, the line between everything that belongs to our sun and everything that belongs to the rest of the galaxy. In 2012, Voyager 1 crossed that line and kept transmitting from the other side. For the first time in human history, we had a working instrument sitting in interstellar space, the region between star systems. No telescope on Earth can truly experience that environment from the inside. No computer model built from data collected here at home can fully capture what it actually feels like out there. Voyager 1 could, because it was actually there, and what it started sending back did not match what scientists had spent decades predicting. For years before Voyager 1 arrived at that boundary, researchers had built detailed models describing what interstellar space should look like. Those models mostly agreed on one thing: it should be calm. A thin, quiet, mostly empty region where particles drift slowly and not much happens. Voyager 1 found something very different. Starting around 2017, an instrument on board began picking up a strange, steady signal in the plasma surrounding the spacecraft. Not a one-time spike, not a glitch that engineers could explain away and move past. A continuous hum that kept showing up, year after year, stretching across hundreds of millions of miles of space. Researchers who published their findings in a peer-reviewed astronomy journal described interstellar space as more active and more textured than earlier models suggested. It appears to have structure, motion, and complexity at almost every scale, from tiny distances up to distances measured in the millions of miles. In simple terms, the empty space between stars might not be empty at all. It might be closer to a quiet ocean with hidden currents running through it. Currents we never knew existed until a spacecraft actually sailed into them. Here is why this matters beyond pure curiosity. That same protective bubble that Voyager 1 punched through is the same bubble shielding life on Earth. The heliopause helps block high-energy cosmic radiation coming from distant exploded stars, keeping the most dangerous particles from reaching the inner solar system at full strength. If that boundary behaves in ways our models never predicted, researchers say we may need to rethink how stable that shield really is over long stretches of time. Scientists are careful not to say Earth is in immediate danger, but they are increasingly saying we understood this protective layer less than we thought we did, and that gap in knowledge matters, because that layer has quietly protected every living thing on this planet for billions of years. Now here is where the story gets harder to believe, because in November 2023, Voyager 1 nearly went silent for good. For roughly 5 months, the spacecraft kept transmitting a signal, but the signal made no sense. Engineers at NASA's Jet Propulsion Laboratory, people who had spent their careers reading this spacecraft's data, could not decode a single readable word from it. The instrument was alive, the connection was alive, but whatever it was trying to say had turned into digital noise. Eventually, engineers traced the problem to a single memory chip that had physically worn down after nearly 5 decades of constant radiation exposure. One tiny component, smaller than a fingernail, had quietly failed and corrupted the part of the software responsible for formatting outgoing data. Under normal circumstances, you would simply walk over and replace a broken chip. This chip was more than 15 billion miles away. There was no repair mission, no backup part, and no way to physically touch the spacecraft ever again. The only tool available was a radio signal, and even that signal took about 22 hours to travel one way. Every single test the team ran required roughly 44 hours just to send an instruction and receive a response. Engineers would form a theory, write new commands, transmit them, and then simply wait almost 2 full days to learn if they were right or wrong. One incorrect command sent across that distance could have ended the mission permanently, with 0 chance of recovery. After months of this painstaking process, the team found a solution. They could not fix the damaged section of memory, but they could move the corrupted code elsewhere, splitting it into smaller pieces and storing them in different parts of the spacecraft's remaining memory. By mid-2024, Voyager 1 came back online, sending clear, readable data once again. And almost immediately, it resumed sending back more of that mysterious plasma signal from interstellar space, the very anomaly researchers still hadn't explained. But none of that fully prepared scientists for what the original 2012 crossing had actually revealed about the boundary itself. For decades, models predicted a smooth, gradual transition at the heliopause, similar to a river slowly blending into the ocean. That is not what the data showed. Instruments recorded particles moving at extraordinary speeds, colliding with enough energy to generate temperatures researchers compared to tens of thousands of degrees Celsius, right at the edge of our solar system. Some scientists have nicknamed this region a wall of energy because it behaves less like a gentle border and more like an active, violent transition zone. Then came an even bigger surprise involving magnetism. Researchers had long assumed the Sun's magnetic field and the galaxy's magnetic field were 2 separate systems, cleanly divided at the heliopause. Instead, Voyager 1's data suggested the 2 fields are connected, linked through a process called magnetic reconnection, where field lines from different sources merge and release energy. That means our solar system is not magnetically isolated from the rest of the galaxy. It is, in some sense, plugged into it. Researchers say this discovery alone could force a rewrite of how we understand the long-term relationship between our solar system and the wider cosmos. Now let's talk about what is happening this year, because Voyager 1's story is not finished. Its power comes from 3 generators that convert the heat of slowly decaying plutonium into electricity. At launch, those generators produced around 470 watts. Today, they produce a small fraction of that, and the output drops by a few watts every single year. Sometime in the early 2030s, researchers expect the power will drop below the level needed to run any instrument at all. Of the 10 scientific instruments Voyager 1 originally carried, most have already been switched off to conserve power, including one shut down earlier this year that had been running almost continuously since launch. But engineers have not given up. NASA teams are reportedly testing an experimental method to redistribute power more efficiently across the spacecraft's aging systems, hoping to squeeze out extra operating time. Because the procedure carries real risk, engineers are testing it first on Voyager 1's sister spacecraft, Voyager 2, before attempting it on Voyager 1 itself. If it works, there is a real possibility that at least one shutdown instrument could be switched back on, giving researchers more precious data before the mission finally goes quiet. There is also a specific date on the calendar that researchers have been quietly counting down to. In November 2026, Voyager 1 is expected to become the first human-made object to reach a distance of exactly 1 light day from Earth. That means a radio signal, traveling at the fastest speed physically possible, will take a full 24 hours just to reach the spacecraft, and another 24 hours for any reply to come back. No human object has ever been that far away while still transmitting, and Voyager 1 will keep moving past that point, roughly 38,000 miles farther every single hour, for as long as its power holds out. Attached to the spacecraft is something that will likely outlast the mission itself by unimaginable amounts of time. It's a gold-plated record, carrying greetings in dozens of human languages, recordings of ocean waves, birdsong, human laughter, and roughly 90 minutes of music from cultures around the world. Astronomer Carl Sagan, who helped design it, once described it as a message sent out like a bottle into a cosmic ocean. Long after Voyager 1 stops transmitting, long after every city and every written record on Earth has faded away, that small golden disk will likely still be drifting through space, carrying proof that something curious once lived here. Here's the part of the story that scientists still can't fully close. That strange plasma signal detected since 2017 has 2 possible explanations, and researchers have not yet determined which one is correct. One possibility is that it comes from ordinary plasma oscillations, a known physical process that would confirm existing theories rather than overturn them. The other possibility is something called quasi-thermal noise, a different mechanism that would require scientists to meaningfully revise their models of interstellar space. Answering this question would likely require either more data from Voyager 1 itself, which is limited, or a brand new mission specifically built to study interstellar space. No such mission currently exists, and none is currently funded. Even if one were approved today, researchers estimate it would take roughly 25 years just to reach the heliopause, which means when Voyager 1 finally falls silent sometime in the early 2030s, this open question may stay open for an entire generation. Right now, in 2026, the only working scientific instrument humanity has ever placed in interstellar space is nearly 50 years old, built with technology that predates the personal computer and running on less power than most household appliances. And it is still teaching us things no telescope on Earth has ever been able to teach us. Researchers say some questions about the universe can only be answered from inside it, not from a lab, not from a satellite, but from a machine that actually crossed that boundary and kept talking. We have exactly one machine like that, and for however many more years it keeps transmitting, the real question is simple. Is anyone still listening closely enough to hear what it's trying to tell us before the signal finally goes quiet?